Alright, we've come nearly to the end of our course. What I'd like to do now is summarize what I think are the high points, that is, the most important testing principles that I've tried to convey in this course, and put them all in one place. So let's go through these. First of all, testers must want software to fail. Second, testers are like detectives who are hunting down bugs. And as detectives, testers have to be observant to all sorts of suspicious behaviors and anomalies in the software under test. My guess is that a number of really serious bugs that have occurred over the years are things that had already been noticed by people and swept under the rug because the people were busy, they just wanted to ship the product, or maybe they were users who didn't know what the bugs meant. So regular users have the luxury of ignoring bugs, but testers don't. And so it's really important not to sweep things under the rug. All available test oracles should be used as a basis for testing. And so you might be tempted to think from the language that I was using, that is strong oracles versus weak ones, that if we had a couple of good strong oracles available, maybe we wouldn't need the weak ones. Maybe we just wouldn't use them at all. And as I hope I've convinced you by now, that's not the case at all. All of the oracles should be used because they can all generally detect different kinds of faults, and even if they detect the same faults, weak oracles might be much cheaper to use. Test cases should contain values selected from the entire input domain. And if there's doubt about what exactly that domain is, this is something that would be good to hash out with the developers. Interfaces that crossed a trust boundary need to be tested with all representable values, not just those from the ostensible input domain. So if we recall some of the examples we've looked at, if we're writing a web server, we might hope that everybody submits data that's well formatted, but it's most likely the case that they won't. And the reason they won't is they'll be trying to break into our web server. And so we need to test on that kind of data to ensure that we can correctly reject it. Similarly, a piece of software like the Linux kernel has a trust boundary at the system call interface, that is to say, at the interface between user mode applications and the Linux kernel. The Linux kernel, like the web server, can't trust that its clients are going to make well-formed requests all the time. It should expect that its clients, if not actually hostile, are at least buggy and are going to do all sorts of crazy stuff. And it needs to catch that instead of crashing or violating its security policy. A little brute force goes a long ways when we're testing. And what I mean in particular is that in certain restricted circumstances, we can do exhaustive testing, and almost anything else can be randomly tested. Quality cannot be tested into bad software. We saw the Therac 25 example, where the control software for the radiation therapy machine was probably so broken that almost no amount of testing would have been sufficient to make it right. It needed to be thrown away, and they needed to start over. I'm sure we've all seen software that looked like that. So in contrast with examples like the Therac 25, testable software has a few of the following qualities. No hidden coupling between modules, and side channels where modules can share information without being visible to the system developers. Few variables that are shared between threads. Few global variables shared between modules, and no pointer soup. And that is to say, no huge data structures with pointers going everywhere, where we can't possibly keep track of who's changing what and what's valid and what's not. Code should be self-checking whenever possible, using plenty of assertions. However, these assertions are never used for error checking. Rather, they're used to check for logically impossible conditions that imply some sort of an internal consistency violation. Assertions must never be side-effecting, because if they are, and you turn them off, the system behavior will change, and this leads to madness among developers. Finally, these assertions should never be silly or trivial ones. Because first of all, those serve no purpose. Second, they clutter up code. Third, they make things slower. And finally, they fail to communicate useful information to the next person who looks at the code. When appropriate, all three sources of input to a piece of software under test should be used as a basis for testing. And those include the obvious APIs provided by the software under test, which can be tested directly. APIs used by the software under test can be tested using fault injection techniques. So recall that these are things like substituting the library that provides these APIs with a different library that injects faults, or perhaps just hacking the layer underneath to inject faults. Finally, non-functional inputs, such as thread schedules, need to be tested using whatever method you can get that will work to actually test these things. And finally, the last principle for testing is that failed code coverage do not provide a mandate to cover the failed items, no matter how tempting that might be, but rather they give clues to ways in which the test suite is inadequate. So blindly coding to the coverage metric is going to destroy those clues, but it's going to do it in such a way that doesn't improve the quality of the test suite very much. So taken together, this list of items that I've just given you constitutes pretty much all that I know about testing. And the detailed version of these has been the content of this course. And this is material that I haven't ever taught before, so I hope it came out in sort of a fairly coherent fashion. It's stuff that's been brewing in my mind for a long time. I've wanted to teach it because I've noticed for years that we don't seem to be doing a very good job teaching CS students to test. What happens instead is they write small test cases in response to assignments. They debug them till they pass the test cases we give them, hand them in, and never look at them again. And it's hard to think of anything less like the real world of software development than the environment we create in classes. So what I've tried to do is structure this course a little bit differently, try to bring out things that I feel are really important that we often don't do a very good job with. And this has been really enjoyable for me. It's been great to actually try to set this material down in a coherent fashion. And I very much hope that this material has been useful for you and that the class has been enjoyable. Thank you.